Look in one direction in space and measure the temperature of the ancient light from the edge of the observable universe. Now, look in the opposite direction. The temperature is exactly the same, not close, identical. These two regions are separated by over 90 billion light years, and they've never been in contact, never exchanged information, never communicated, and yet they're identical. This shouldn't be possible. There hasn't been enough time since the Big Bang for these regions to influence each other to reach the same temperature. This is the horizon problem, one of the deepest mysteries in cosmology. If understanding how the universe became so perfectly uniform sounds fascinating, a quick subscribe would mean the world to me, and drop a comment letting me know where you're watching from. Let's explore the impossible uniformity of the cosmos. To understand the horizon problem, you first need to understand what we're actually observing when we look at the universe. When you look up at the night sky, you see stars and planets and galaxies. But there's something else out there that you can't see with your eyes. A faint glow of microwave radiation coming from every direction. This is the cosmic microwave background, the CMB, and it's the oldest light in the universe. This light was emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could finally travel freely through space. Before that moment, the universe was so hot and dense that light couldn't travel far. It would immediately scatter off the free electrons filling space. The universe was opaque, like being inside a thick fog. But when atoms formed, the electrons got bound to nuclei. Light could suddenly travel without scattering. The universe became transparent, and the light that started traveling at that moment is what we detect today as the cosmic microwave background. This light has been traveling toward us for over 13 billion years. It's been stretched by the expansion of the universe from visible light into microwaves. When we detect it with radio telescopes, we're seeing a snapshot of what the universe looked like 380,000 years after the Big Bang. And here's what's remarkable. This light comes from every direction in space. No matter where you point your telescope, you detect this glow. It surrounds us completely, a sphere of ancient light marking the edge of the observable universe. And when you measure the temperature of this light, the temperature of the universe at that early time, you find something astonishing. It's the same everywhere, 2.725 Kelvin. That's minus 270 degrees Celsius, just a few degrees above absolute zero. And this temperature is uniform across the entire sky to an incredible precision. The first detailed measurements of the cosmic microwave background came from a satellite called COBE, the Cosmic Background Explorer, launched in 1989. COBE mapped the temperature of the CMB across the entire sky, and what it found was uniformity. The temperature varied by only about 1 part in 100,000 from one direction to another. That's like measuring the temperature in your room and finding that one corner is exactly 20 degrees Celsius and another corner is 20.0002 degrees. Virtually identical. Later, satellites, WMAP and Planck measured the CMB with even greater precision and found the same thing: uniformity. The entire universe, at least the part we can observe, was at the same temperature 380,000 years after the Big Bang. Why is this a problem? Why is uniformity surprising? Because temperature uniformity requires communication. If you have two objects at different temperatures and you put them in contact, they'll exchange heat until they reach the same temperature. This is called thermal equilibrium. Hot coffee in a cold room will cool down. The coffee loses heat to the air. The air gains heat from the coffee. Eventually, they reach the same temperature, but this requires contact, requires interaction, requires the ability to exchange energy. Two objects that never interact will never reach thermal equilibrium. They'll stay at whatever temperatures they started with. And here's the problem. Different regions of the observable universe have never been in contact. They've never exchanged energy. They've never communicated. And yet, they're at the same temperature. How is this possible? To understand why this is such a profound mystery, we need to understand the cosmic horizon. The horizon in cosmology is similar to the horizon you see when you look at the ocean. You can only see so far. Beyond a certain distance, the curvature of the earth blocks your view. Ships beyond the horizon are invisible. In cosmology, the horizon is set not by the curvature of the earth, but by the speed of light and the age of the universe. Light travels at a finite speed, about 300,000 kilometers per second. In the time since the Big Bang, about 13.8 billion years, light has traveled a finite distance. This distance defines our cosmic horizon. We can only see objects whose light has had time to reach us. Objects beyond the horizon are invisible, not because they don't exist, but because their light hasn't reached us yet. The universe might extend infinitely far. We don't know, but we can only observe the part within our horizon. Now, here's where it gets interesting. The horizon works both ways. Just as we can only see objects within our horizon, those objects can only see us if we're within their horizon. Two objects on opposite sides of our observable universe are beyond each other's horizons. The light from one hasn't had time to reach the other. They're causally disconnected. Events in one region cannot influence the other region. There's no way for them to communicate, no way to exchange information or energy, no way to reach thermal equilibrium. And yet, they're at the same temperature. This is the horizon problem. Regions of the universe that should have independent, unrelated temperatures are somehow identical. Let me give you an analogy to make this clearer. Imagine two people living on opposite sides of the earth who have never communicated. They've never met. They've never exchanged letters or phone calls. They don't even know each other exists. Now, imagine you visit both of them and you discover they've both decorated their living rooms in exactly the same way. Same furniture, same paint colors, same artwork on the walls, same arrangement of everything, down to tiny details. This would be extraordinary. How did this happen? Either it's an incredible coincidence, which is extremely unlikely, or there's some connection between them you don't know about. Maybe they both got their ideas from the same source. Maybe they had a common influence. Something must explain the correlation. Random chance just doesn't work when the similarity is so precise. The horizon problem is like this, but more extreme. It's like discovering that billions of people all over the universe, people who have never communicated and can never communicate, all decorated their rooms identically, not just similar. Identical. This demands an explanation. The speed of light is central to this problem because it sets an absolute limit on how fast information can travel. Nothing can go faster than light. This isn't a technological limitation, It's not something we might overcome with better engineering. It's a fundamental law of physics built into the structure of space-time itself. Einstein showed this in his theory of special relativity over a century ago. The speed of light is a cosmic speed limit, and this limit matters for our problem because it means that regions of space can only influence each other if they've had time for light to travel between them. If two regions are so far apart that light hasn't had time to travel from one to the other since the Big Bang, then they've never influenced each other. They're causally disconnected. And causally disconnected regions shouldn't be at the same temperature. Let's do some math to see exactly what the problem is. The universe is about 13.8 billion years old. In that time, light has traveled about 13.8 billion light years. Actually, it's more complicated than that because the universe is expanding, but let's keep it simple for now. If light has traveled about 14 billion light years since the Big Bang, then the maximum distance over which regions could have communicated is about 14 billion light years. Any two regions more than about 14 billion light years apart have never been in causal contact. They're beyond each other's horizons. Now, look at the observable universe. The most distant regions we can see, the regions that emitted the cosmic microwave background we detect today, are about 46 billion light years away from us in each direction. That's because the universe has been expanding while the light was traveling toward us. So, the total width of the observable universe is about 92 billion light years. Two regions on opposite sides of the observable universe are 92 billion light years apart. But they could only have communicated if they were within about 14 billion light years of each other at the time the CMB was emitted. They're way beyond each other's horizons, way beyond the distance light could have traveled, and yet they're at the same temperature. Actually, it's worse than that. The problem is even more severe if you go back to the time when the CMB was emitted. 380,000 years after the Big Bang, the universe was much smaller than it is today. It's expanded by a factor of about 1,000 since then. So, at that time, the regions we're talking about were closer together. But here's the catch. The amount of time available for communication was also much less. Only 380,000 years instead of 13.8 billion years. When you do the calculation properly, taking into account the expansion of the universe and the finite age at that time, you find that regions separated by more than a few degrees on the sky should never have been in causal contact. They should be independent, random, uncorrelated, but they're not. They're identical. The entire sky, all 360 degrees, is at the same temperature. Regions separated by 180 degrees, opposite sides of the sky, are at the same temperature. This is impossible according to standard cosmology. There's no way for these regions to have communicated. No way for them to reach thermal equilibrium. No way for them to become uniform. This is what makes the horizon problem so profound. It's not just a minor discrepancy or a small unexplained detail. It's a fundamental contradiction between what we observe and what the laws of physics allow. The universe is uniform when it shouldn't be. The temperature is the same everywhere when it should be different in different places. This tells us that something is wrong with our understanding. Either our observations are incorrect, which seems unlikely given how precisely we've measured the CMB, or our theory of the early universe is incomplete. Something must have happened in the very early universe that we don't understand. Something that allowed distant regions to communicate and reach the same temperature before they became causally disconnected. This something is what we're trying to figure out. Let me emphasize how precise this uniformity is, because it's really quite remarkable. When I say the temperature is the same everywhere, I don't mean it's roughly the same or approximately the same. I mean it's the same to a precision of 1 part in 100,000. The average temperature is 2.725 Kelvin. The variations around this average are only about 30 millionths of a Kelvin. That's like saying the temperature in your room is 20 degrees in one corner and 20.00003 degrees in another corner. You'd need an extremely sensitive thermometer to detect that difference. The universe, at the time the CMB was emitted, was uniform to this incredible precision across regions that should never have been able to influence each other. This isn't just uniform, it's suspiciously uniform, unnaturally uniform, the kind of uniformity that demands an explanation. To make matters even more puzzling, the small variations that do exist in the CMB temperature are also interesting. They're not random. They have a pattern, a specific statistical distribution. These variations are the seeds of structure in the universe. Regions that were slightly denser than average went on to form galaxies and clusters of galaxies. Regions that were slightly less dense became voids. The entire large-scale structure of the universe, all the galaxies and galaxy clusters and superclusters, grew from these tiny variations in the early universe. And here's what's amazing. These variations are the same everywhere. The statistical properties of the hot and cold spots in the CMB are identical in all directions. Again, this requires some kind of coordination, some mechanism that ensured the entire universe started with the same statistical properties. Without such a mechanism, different regions would have different patterns, different amounts of clumpiness. But they don't. It's all the same. The horizon problem isn't just about temperature. It's about all the properties of the early universe. The density was uniform. The expansion rate was uniform. The amount of matter versus antimatter was uniform. The physical constants, like the strength of gravity and electromagnetism, were uniform. Everything was the same everywhere. This universal uniformity is what needs explaining. It's not enough to explain why the temperature is uniform. We need to explain why everything is uniform, why the entire universe looks like it came from the same initial state despite being composed of regions that could never have communicated with each other. This brings us to the question of initial conditions. When the Big Bang happened, what determined the initial state of the universe? Why did it start uniform? Why didn't different regions start with different temperatures or densities or properties? In principle, the Big Bang could have produced a chaotic, messy, non-uniform universe. Random fluctuations could have created regions with wildly different conditions. And without some mechanism to smooth things out, those differences should still be visible today. But the universe isn't chaotic. It's ordered, uniform, smooth. This smoothness must have been built into the initial conditions. The Big Bang must have produced a uniform universe from the start. But why? What determined those initial conditions? This is one of the deepest questions in cosmology. The horizon problem forces us to confront it, forces us to ask not just how the universe evolved, but how it began, what set the stage for everything that followed. Some people might wonder if the uniformity could just be a coincidence. Maybe the universe randomly happened to start in a uniform state. Maybe we just got lucky. But this explanation doesn't hold up when you think about it carefully. The probability of the universe randomly starting in such a uniform state is extraordinarily low. Imagine flipping a coin a trillion times and getting heads every single time. That's roughly the kind of improbability we're talking about. Technically possible, but so unlikely that it doesn't make sense to invoke chance. When you see such an unlikely outcome, you should look for a reason. Some mechanism or process that makes it likely instead of unlikely. Something that explains the uniformity rather than dismissing it as luck. This is what physicists mean when they talk about fine-tuning. The universe appears to be fine-tuned for uniformity. The initial conditions were set with incredible precision to produce the smooth, uniform cosmos we observe. And fine-tuning demands explanation. It suggests something interesting is going on, something we need to understand. The horizon problem was recognized in the 1970s as cosmologists began to understand the implications of the Big Bang theory and the finite speed of light. The standard Big Bang model, developed in the decades after Edwin Hubble discovered the expansion of the universe, assumed the universe started from a hot, dense state and has been expanding and cooling ever since. This model explained a lot. It explained why the universe is expanding. It explained the cosmic microwave background. It explained the abundance of light elements like hydrogen and helium. But it didn't explain why the universe was so uniform. In fact, the Big Bang model made the uniformity seem impossible. If you start with the standard Big Bang and work forward in time, there's no way for distant regions to communicate and become uniform. They start out causally disconnected and stay that way. So, where did the uniformity come from? This was a serious problem, not a minor detail, but a fundamental flaw in our understanding. For a while, physicists simply accepted the uniformity as an initial condition. They said the universe just started uniform and left it at that. This was unsatisfying, but there didn't seem to be an alternative. You had to start with some initial conditions. Why not assume uniform initial conditions? But this felt like giving up. Like sweeping the problem under the rug. It didn't explain anything. It just labeled the problem as unexplainable, and most physicists felt there should be a deeper explanation. The uniformity was too precise, too unlikely to be just an arbitrary initial condition. There had to be a physical process that created it, something that happened in the very early universe before the regions became causally disconnected. Some era when the universe was small enough that all the regions we now observe were in causal contact. During that era, they could have reached thermal equilibrium, become uniform. Then, as the universe expanded, they moved outside each other's horizons. But the uniformity persisted. It was imprinted during that early contact phase. This is the essence of the solution to the horizon problem. Find a mechanism that allows early universe regions to communicate and become uniform before they get separated by the expansion. This mechanism exists. It's called inflation. But before we get to inflation, let's fully appreciate the problem. let's understand exactly why the standard Big Bang doesn't work and what constraints any solution must satisfy. The standard Big Bang model makes specific predictions that we can test. It tells us how the universe should evolve from a hot, dense state, how it should expand, how it should cool, how light elements should form in the first few minutes, how the cosmic microwave background should form when atoms first appear. All of these predictions have been confirmed. The Big Bang model works incredibly well for explaining what happened after the first second or so. But it doesn't tell us about the very beginning. It doesn't tell us about the initial conditions. It just starts with those conditions and moves forward. And the initial conditions it requires, specifically the uniformity, are impossible to achieve within the model itself. This is the deep problem. The model can't explain its own starting point. Let me walk through exactly what happens in the standard Big Bang timeline to show you where the problem arises. At the very beginning, time zero, the universe is infinitely hot and dense. This is a singularity, a point where our physics breaks down. We can't describe what's happening at the singularity itself, but we can describe what happens immediately afterward. In the first fraction of a second, the universe expands and cools rapidly. Different forces that are unified at high temperatures separate into distinct forces. Particles and antiparticles are created and annihilate each other. It's an extremely energetic, chaotic environment. By about 1 microsecond, the universe has cooled enough that quarks can combine to form protons and neutrons. By about 1 second, it's cool enough that neutrinos stop interacting with other particles and begin traveling freely through space. By about 3 minutes, nuclear fusion begins creating helium and other light elements from hydrogen. This lasts for about 17 minutes, then stops as the universe cools below the temperature needed for fusion. At this point, the universe is about 75% hydrogen and 25% helium by mass, with trace amounts of other light elements. This matches what we observe in the oldest stars today, which is strong evidence the Big Bang model is correct. For the next 380,000 years, the universe continues expanding and cooling. It's filled with ionized plasma, free electrons and nuclei. Light can't travel far in this plasma. It scatters constantly off the free electrons. The universe is opaque. Then, at about 380,000 years after the Big Bang, the universe cools enough for electrons to bind to nuclei and form neutral atoms. This is called recombination. When recombination happens, the universe suddenly becomes transparent. Light can travel freely. The photons that were constantly scattering off electrons are suddenly released. They begin a journey through space that continues to this day. These are the photons we detect as the cosmic microwave background. The CMB is a snapshot of the universe at the moment of recombination. It shows us what conditions were like at that time, and what it shows is uniformity. Perfect, precise, impossible uniformity. Now, let's think about the causal structure of this timeline. For any event in space-time, there's a region called the past light cone. This is the set of all events that could have influenced this event by sending light or information. Events outside the past light cone are too far away. Light from those events hasn't reached this event yet, so those events couldn't have influenced what's happening here. Every point in space at every moment in time has a past light cone. The size of the past light cone depends on how much time has elapsed. The longer the time, the larger the past light cone. In the early universe, when only a short time had elapsed since the Big Bang, the past light cones were small, very small. Any given region of space could only have been influenced by a small region around it. Regions farther away were outside the past light cone, causally disconnected. At the time of recombination, 380,000 years after the Big Bang, let's consider 2 points in the universe that are now on opposite sides of the observable universe. Back then, the universe was about 1,000 times smaller, so these points were much closer together. But they were still very far apart, and crucially, their past light cones didn't overlap. Events in one region couldn't influence the other region. There wasn't enough time for light to travel between them. They were causally independent. Whatever temperature one region had was determined by its local conditions. Whatever temperature the other region had was determined by its local conditions. There's no way for them to have communicated and agreed on a common temperature. And yet, when we measure the CMB from these two regions today, we find they were at exactly the same temperature. How is this possible? Let me give you some specific numbers to make this more concrete. At recombination, the observable universe was about 84 million light-years across. But the maximum distance light could have traveled since the Big Bang was about 1 million light-years. This is because even though 380,000 years had passed, the universe was expanding during that time, which affects how far light could travel. The ratio of the observable universe size to the light travel distance was about 84:1. This means the observable universe was divided into about 84 cubed, or about 600,000 causally disconnected regions. Each of these regions should have been independent, random, uncorrelated, but they weren't. They were all at the same temperature. All 600,000 regions somehow coordinated to have identical conditions despite never having communicated. This is the horizon problem quantified. It's not just that a few regions are the same. It's that hundreds of thousands of independent regions are identical. The implications of this are staggering. It means the Big Bang must have started with these 600,000 regions already uniform, already at the same temperature, already coordinated. But how? What set those initial conditions? The Big Bang model itself doesn't answer this. It just assumes uniformity and moves on. But assuming uniformity is deeply unsatisfying because uniformity is so unlikely, so improbable, so special. It's like assuming the answer to the puzzle instead of solving the puzzle. We want to understand why the universe is uniform. What mechanism created the uniformity? Simply declaring it as an initial condition doesn't explain anything. It just labels the mystery as fundamental and unexplainable. And scientists don't like unexplainable mysteries. We want mechanisms, processes, physical reasons for why things are the way they are. This brings us to anthropic reasoning, which some people invoke to explain fine-tuning. The anthropic principle says that we shouldn't be surprised to find ourselves in a universe that's compatible with our existence, because if the universe weren't compatible, we wouldn't be here to observe it. Applied to the horizon problem, the anthropic argument would say that only a uniform universe could give rise to galaxies and stars and planets and life. A non-uniform universe would be too chaotic, too lumpy, Structure would form in some regions but not others. Most regions would be inhospitable. Only uniform universes like ours can support observers like us. So, of course, we observe a uniform universe. We're selected to be in one by the requirement that we exist. This is clever, but most physicists find it unsatisfying. It doesn't explain why our universe is uniform. It just says that if it weren't, we wouldn't be here. But there could be many other uniform universes with different properties. The anthropic principle doesn't tell us why our universe has the specific properties it does. It doesn't predict anything. It doesn't give us a mechanism. It's more of a philosophical observation than a scientific explanation. Most physicists prefer mechanistic explanations, physical processes that create the observed phenomena, and for the horizon problem, such a mechanism exists. Inflation. But before we get to inflation, let's talk about the other initial condition problems the Big Bang model has, because they're all related. The horizon problem isn't the only fine-tuning issue in cosmology. There's also the flatness problem. This is the observation that the geometry of space is very close to flat. Einstein's general relativity tells us that space can be curved. It can be like the surface of a sphere where parallel lines converge. This is called positive curvature or closed geometry. Or it can be like a saddle shape where parallel lines diverge. This is negative curvature or open geometry. Or it can be flat, like a plane, where parallel lines stay parallel. This is zero curvature or flat geometry. Measurements of the cosmic microwave background tell us our universe is flat to within about 0.5%. It might be slightly curved, but it's very close to flat. And here's the puzzle. Flat geometry is unstable in the expanding universe. Any small deviation from flatness grows over time. If the universe starts slightly curved, it becomes more curved as it expands. For the universe to be so close to flat today, it must have been incredibly close to flat in the early universe. So close that the deviation from flatness was less than 1 part in 10 to the 60th. That's a decimal point followed by 59 zeros, then a 1. This is extreme fine-tuning. The initial curvature had to be set with extraordinary precision. Why? What determined this precision? The Big Bang model doesn't explain it. It just assumes it. Another unexplained initial condition. There's also the magnetic monopole problem, though this is more of a prediction of particle physics than an observation. Some theories of particle physics predict that magnetic monopoles, particles with just one magnetic pole, north or south, should have been created in the early universe. And not just a few. Enormous numbers of them, so many that they should dominate the mass of the universe today. But we don't observe any magnetic monopoles. None have ever been detected. Where did they go? Or why weren't they created? Again, the Big Bang model doesn't explain this. It predicts monopoles should exist, but they don't. Something must have prevented their creation or gotten rid of them. But what? All three of these problems, the horizon problem, the flatness problem, and the monopole problem, point to the same conclusion. The standard Big Bang model is incomplete. It's missing something, some process or event in the very early universe that set the initial conditions. That made the universe uniform and flat and free of monopoles. This process, whatever it is, must have operated before the standard Big Bang timeline begins, before the first second, before the first microsecond. In the earliest moments of the universe, when conditions were so extreme that normal physics breaks down, This is where inflation comes in. But inflation is the solution, not the problem. First, let's make sure we fully understand the problem. Let's make sure we appreciate just how mysterious and profound the horizon problem really is. Because once you understand the problem deeply, the solution becomes even more impressive. Think about what it means for the universe to be uniform. It means every region has the same properties, same temperature, same density, same expansion rate, same physical laws. This uniformity extends to properties we can measure and properties we can't. The constants of nature, like the speed of light and the strength of gravity, are the same everywhere, at least as far as we can tell from astronomical observations. The laws of physics are the same everywhere. Chemical elements behave the same way in distant galaxies as they do here. This universality of physical law is something we usually take for granted. But it's remarkable. Why should the laws of physics be the same everywhere? Why shouldn't different regions have different laws, different constants, different behaviors? The fact that physics is universal suggests the entire universe has a common origin, a common cause. Everything we see came from the same source, inherited the same properties. This is what the horizon problem is really telling us. The universe has a unified origin. It's not a collection of independent regions that happen to look similar. It's a single system that started from a single state. And understanding that single state, that common origin, is the key to solving the horizon problem. The precision of the uniformity is also worth dwelling on. 1 part in 100,000 for the temperature variations in the CMB. This is astonishingly precise. It's like taking 1,000,000 random numbers and finding they're all the same to 5 decimal places. Random processes don't produce this kind of precision. Random fluctuations create variations, differences, diversity. To get uniformity this precise, you need a mechanism that enforces it. That drives the system toward a uniform state. That suppresses variations. In thermodynamics, this mechanism is thermal equilibrium. Objects exchange energy until they reach the same temperature. But thermal equilibrium requires contact, requires interaction, requires time. The horizon problem is that there wasn't enough time. The regions couldn't have reached equilibrium, and yet they did. Somehow, some other mechanism must have created the uniformity, something faster than thermal equilibrium, something that worked on timescales shorter than the light travel time. This is what makes inflation so powerful. It provides exactly this mechanism. But we're getting ahead of ourselves. First, the problem, then the solution. Let's explore what measuring the cosmic microwave background actually involves, because understanding the observations helps us appreciate the problem. The CMB was first detected accidentally in 1965 by Arno Penzias and Robert Wilson, 2 radio astronomers working at Bell Labs in New Jersey. They were trying to use a large horn antenna to detect radio signals from the Milky Way, but they kept picking up mysterious noise. A constant hiss coming from every direction. They thought it might be interference from nearby New York City or perhaps contamination in their antenna. They even cleaned out pigeon droppings from the antenna thinking that might be the source, but the noise persisted. It was always there, same intensity, same frequency, coming from every direction. Eventually they realized what they were detecting was something cosmic, radiation from space. and not just from specific sources like stars or galaxies. It was coming from everywhere. The entire sky glowed with this radio noise. They had discovered the cosmic microwave background. This discovery was revolutionary. It provided direct evidence for the Big Bang. The universe really did have a hot, dense beginning. The CMB is the afterglow of that beginning, the cooled remnant of the Big Bang. Penzias and Wilson won the Nobel Prize in Physics for this discovery in 1978. Their initial measurements were crude. They could only determine that the CMB existed and had a temperature of about 3 Kelvin. They couldn't measure variations in temperature across the sky. They didn't have the sensitivity. For that, you need satellite-based instruments above the Earth's atmosphere where interference is minimal. The first such satellite was COBE, launched by NASA in November 1989. COBE had instruments designed to measure the CMB with unprecedented precision. It would map the temperature of the CMB across the entire sky. Look for variations. Look for structure. The team spent years carefully analyzing the data, removing foreground contamination from our galaxy, accounting for instrumental effects. And in 1992, they announced their results. The CMB was uniform. The temperature was 2.726 Kelvin everywhere, but there were tiny variations, hot and cold spots. The variations were only about 30 millionths of a Kelvin, 1 part in 100,000. This was exactly what the Big Bang model predicted. If the early universe had been perfectly uniform with no variations at all, no structure would have formed, no galaxies, no stars, no us. The tiny variations in the CMB are the seeds of all structure. Regions that were slightly denser became even denser as gravity pulled in more matter. Over millions and billions of years, these over-dense regions collapsed into galaxies and galaxy clusters. The entire cosmic web of structure we see today grew from these microscopic variations at recombination. The COBE results were groundbreaking, but the resolution was limited. COBE could only see large-scale features, variations spread across many degrees of sky. To see finer details, you need better instruments. In 2001, NASA launched WMAP, the Wilkinson Microwave Anisotropy Probe. WMAP had higher resolution and higher sensitivity than COBE. It could measure variations on smaller angular scales. See more detailed patterns. WMAP operated for 9 years, from 2001 to 2010, producing increasingly precise maps of the CMB. It confirmed COBE's results, but with far greater detail. The temperature variations had a specific pattern, a specific power spectrum. This pattern contained information about the universe, the geometry of space, the amount of normal matter, the amount of dark matter, the amount of dark energy, the age of the universe. All of this information is encoded in the tiny temperature variations of the CMB. By analyzing these variations, cosmologists could measure the fundamental parameters of our universe with unprecedented accuracy. Then, in 2009, the European Space Agency launched Planck, an even more capable satellite. Planck observed the CMB for 4 years with the highest resolution and sensitivity yet achieved. It produced the definitive map of the cosmic microwave background. Every measurement confirmed what COBE and WMAP had found. The universe is uniform. The variations are tiny. The pattern matches the predictions of the Big Bang model plus a particular model of structure formation. Everything fits together. The observations are consistent, and the uniformity. The impossible uniformity that the horizon problem highlights is confirmed with extraordinary precision. We're not guessing, we're not speculating, we've measured it, mapped it, analyzed it. The universe really is this uniform, and it really does present a profound puzzle. When cosmologists analyze the CMB data, they decompose the temperature map into spherical harmonics, mathematical functions that describe patterns on a sphere. Think of it like breaking down a musical note into its component frequencies. A trumpet playing middle C produces a fundamental frequency plus harmonics, overtones that give the trumpet its characteristic sound. Different instruments playing the same note have different harmonic content. Similarly, the temperature pattern of the CMB can be described by its harmonic content. The largest scale variations, changes across the entire sky, are the lowest harmonics. Smaller scale variations are higher harmonics. Each harmonic tells us something about the physics of the early universe, the amplitude of the variations at each scale, the phase relationships between different scales. All of this contains information, and what's remarkable is that the observations match the theoretical predictions extremely well. We can calculate what the harmonic pattern should be if the universe started with certain properties and evolved according to known physics. When we compare these calculations to the observations, they agree. This gives us tremendous confidence that we understand the basics of how the universe evolved. But it also sharpens the horizon problem. The uniformity we observe is real, precisely measured, undeniable. And it contradicts the standard Big Bang model. The statistical properties of the CMB variations are also uniform across the sky. This is called statistical isotropy. If you measure the temperature variations in one patch of sky and calculate their statistical properties, the amplitude of variations, the correlation between nearby points, the power at different scales, and then do the same calculation for another patch of sky far away, you get the same results. The statistics are the same everywhere. This is another form of uniformity. Not just that the average temperature is the same, but that the character of the variations is the same. The universe is statistically homogeneous. This isotropy extends beyond what any causal mechanism in the standard Big Bang could produce. Different patches of sky correspond to regions that were never in causal contact, never influenced each other, and yet they have identical statistical properties. This is the horizon problem again, but at a different level. Not just the mean temperature, but the entire distribution. Let me try another analogy to make the profundity of this clear. Imagine you're sampling water from different parts of the ocean. You take a bucket from the Atlantic, another from the Pacific, another from the Indian Ocean. You bring all these samples back to your lab and you analyze them. You measure the temperature, the salinity, the chemical composition, the isotope ratios, and you find they're all identical, exactly the same. Now, this wouldn't be surprising if the ocean were perfectly mixed. If currents circulated the water and brought all parts of the ocean into contact with each other. But imagine the oceans are separated. No currents connect them. They've never exchanged water. They're completely independent. And yet, they're identical. This would be astonishing. It would demand an explanation. Either they had a common source, some original body of water that was divided into separate oceans, or there's some mechanism you don't know about that's keeping them synchronized. The horizon problem is like this, but more extreme. The regions we're talking about couldn't have had a common source. Not in the standard Big Bang model. They've been independent since the beginning, and yet they're synchronized, identical. Something is missing from our understanding. Another way to think about the horizon problem is in terms of entropy. Entropy is a measure of disorder. High entropy means lots of disorder, many possible configurations. Low entropy means order, few possible configurations. A uniform state is a low entropy state. There's only one way to arrange things uniformly, but many ways to arrange them non-uniformly. If you start with a high entropy state, a random mess, and let it evolve with no external influence, it will stay high entropy, random, disordered. To get a low entropy state, a uniform ordered state, you need some mechanism that reduces entropy. That brings order out of chaos. In thermodynamics, this mechanism requires work, energy input. You can't get order for free. You have to pay for it with energy. And the source of that energy has to come from somewhere. In the case of the early universe, what provided the energy to create uniformity? What reduced the entropy? The Big Bang itself started with low entropy. This is sometimes called the past hypothesis. We assume the universe began in a low entropy state. But why? What determined that initial low entropy? This is another version of the horizon problem. Another way of asking about the special initial conditions. The connection between entropy and probability is crucial here. Low entropy states are improbable, unlikely. If you shuffle a deck of cards, you're extremely unlikely to get them in perfect order from ace to king in each suit. But a random jumble is likely, almost certain. There are many more ways to jumble the cards than to order them. Similarly, a uniform universe is improbable. There are many more ways to arrange matter and energy non-uniformly than uniformly. If the Big Bang produced a random initial state, it should have been high entropy, non-uniform, but it wasn't. It was low entropy, uniform. This is backwards from what you'd expect. It suggests the Big Bang wasn't random. Something constrained it. Something enforced the low entropy. And that something is what we're trying to understand. The horizon problem is fundamentally an entropy problem. Why did the universe start with such low entropy? Why was it so ordered? Why was it so special? Some people suggest that maybe we're just wrong about the age of the universe. Maybe it's older than we think. Maybe there was more time for regions to communicate. But this doesn't work. We can measure the age of the universe independently using multiple methods. The expansion rate tells us the age. The oldest stars tell us a lower limit on the age. Radioactive dating of meteorites tells us the age of the solar system, which gives us a lower limit on the age of the universe. All these methods agree. The universe is about 13.8 billion years old. We're not significantly wrong about this. And even if we were off by a factor of 2, it wouldn't solve the horizon problem. The problem is that the observable universe is so much larger than the distance light could have traveled. You'd need the universe to be hundreds of times older to solve the problem by age alone. And that's incompatible with everything else we observe. The age isn't the issue. The issue is that the universe started uniform. And standard Big Bang cosmology can't explain why. Others suggest maybe the speed of light was different in the early universe. Maybe it was faster. If light traveled faster back then, regions could have communicated over larger distances. The horizons would be bigger. But this doesn't work either. Changing the speed of light has consequences. It affects how physics works. If you make the speed of light faster in the early universe, you change how particles interact, how forces propagate, how energy and momentum are conserved. These changes affect nucleosynthesis, the formation of light elements in the first few minutes. They affect when recombination happens. They affect the CMB itself. When you try to make the speed of light faster to solve the horizon problem, you break other things. The model stops agreeing with observations. So, this doesn't work. The speed of light is fixed by the structure of space-time. You can't arbitrarily change it without breaking physics. The philosophical implications of the horizon problem extend beyond physics into questions about the nature of reality and explanation itself. When we do science, we're looking for patterns, regularities, laws that describe how things behave. But underlying those laws are initial conditions, the starting state of the system. In laboratory experiments, we set the initial conditions. We put the system in a known state, then watch it evolve according to physical laws. We can repeat the experiment with different initial conditions and see how the outcome changes. This lets us separate the effects of laws from the effects of initial conditions. But with the universe, we can't do this. There's only one universe. We can't reset it and try different initial conditions. We're stuck with whatever initial conditions actually occurred. This makes cosmology fundamentally different from other sciences. We can measure the laws of physics, test them, verify them. But the initial conditions, those are just given. We observe them, but we can't explain them. Or can we? This is the deep question the horizon problem raises. Are the initial conditions of the universe explainable, or are they simply brute facts? Is there a reason the universe started uniform, or is uniformity just how it happened to be? This distinction matters. If initial conditions are explainable, if there's a mechanism that produced them, then we can understand them scientifically. We can make predictions, test theories, make progress. But if they're brute facts, if they're just arbitrary, then we've reached the limit of scientific explanation. We can only describe what is, not explain why it is. Most physicists believe initial conditions are explainable, at least in principle. The uniformity of the universe isn't arbitrary. It resulted from some physical process, some mechanism operating in the earliest moments. This mechanism is what we're searching for, and inflation, as we'll see, provides exactly such a mechanism. It takes an arbitrary initial state and produces uniformity. It explains the initial conditions rather than assuming them. This is why inflation is so powerful and why it's become the leading theory for the very early universe. It transforms an unexplained mystery into an explained consequence. It turns an assumption into a prediction, and predictions can be tested. This is how science works. This is how we make progress. Not by declaring mysteries unsolvable, but by finding mechanisms that explain them. The horizon problem also connects to the question of why there's something rather than nothing. Why does the universe exist at all? This is perhaps the ultimate question. The existence of the universe seems to require explanation, yet any explanation must itself exist, creating an infinite regress. Some philosophers and theologians argue this points to a necessary being, something that exists by its own nature rather than being caused by something else. Others argue the question is meaningless or unanswerable. But regardless of your philosophical stance, the horizon problem shows that even given that the universe exists, there are deep puzzles about its properties. Not just that it exists, but how it exists, in what state, with what characteristics. The uniformity is one such characteristic, and it demands explanation. Simply saying the universe is uniform because it is doesn't satisfy our desire to understand. We want to know why, what made it that way, and science can potentially answer this not by explaining why something exists rather than nothing, but by explaining why the something that exists has the properties it does. There's also a connection to the concept of naturalness in physics. A theory is considered natural if it doesn't require special, finely tuned parameters. If the theory works for a wide range of parameters, it's natural. If it only works for very specific, carefully chosen parameters, it's unnatural or fine-tuned. The standard Big Bang with uniform initial conditions is unnatural. The initial conditions have to be set with extraordinary precision. A tiny deviation from uniformity would grow over time, and we wouldn't observe the uniform universe we see today. So, the initial state has to be special, fine-tuned. This is a sign that something is missing from the theory. Natural theories don't require fine-tuning. They work robustly for generic conditions. Inflation is natural in this sense. It takes a wide range of initial conditions and produces uniformity. You don't need to fine-tune the starting state. Almost any initial state, as long as it includes a small region where inflation begins, will produce a uniform universe. This naturalness is aesthetically pleasing and, more importantly, scientifically satisfying. It suggests we're on the right track. We found a mechanism that explains the observations without requiring miraculous coincidences. The horizon problem has been called one of the most important unsolved problems that was later solved. It was recognized in the 1970s. Alan Guth proposed inflation as a solution in 1980. Over the following decades, the theory was refined and tested. Today, inflation is the standard paradigm for the very early universe. It's taught in textbooks. It's assumed in most cosmological research. Not everyone agrees with it. There are alternative theories. There are ongoing debates about details. But the basic idea that the universe underwent a period of rapid exponential expansion in its earliest moments is widely accepted. This is because it solves multiple problems simultaneously. The horizon problem, the flatness problem, the monopole problem. It explains the origin of structure. It makes specific, testable predictions that have been confirmed. It's a remarkably successful theory. And it all started with taking the horizon problem seriously, recognizing that the uniformity of the universe isn't something to assume, but something to explain. Understanding the horizon problem changes how you see the universe. You realize that the cosmos isn't just a collection of galaxies and stars and planets. It's a unified system with a common origin. Everything we observe, everything that exists, came from the same initial state, was shaped by the same processes, follows the same laws. This unity isn't obvious from casual observation. When you look at the night sky, you see separate objects, distinct stars, independent galaxies. But at a deeper level, they're all connected, all part of the same story, all descendants of the same ancestor state. The horizon problem reveals this connection by showing that the uniformity can't be coincidence, can't be random chance. It must be the result of a common origin, a shared history, and understanding that history, tracing back to the earliest moments, is what cosmology is all about. It's about understanding where we came from, how we got here, what processes shaped the universe we inhabit. The horizon problem is a signpost pointing us toward those answers. It tells us the standard story is incomplete. Something crucial is missing. And finding that something, understanding it, incorporating it into our cosmological narrative, is one of the great achievements of modern science. The standard Big Bang model, despite its many successes, cannot explain the uniformity we observe. This isn't a minor shortcoming. It's a fundamental gap in our understanding. Several attempts have been made to solve the horizon problem within the framework of standard cosmology, and it's worth understanding why these attempts failed. This helps us appreciate why inflation is necessary and why it works where other ideas don't. One early proposal was that maybe the universe started with uniform conditions, and we should just accept this as given. This is what's called the initial conditions approach. You simply declare that the Big Bang produced a uniform universe and move on. But as we've discussed, this is deeply unsatisfying. It's not an explanation, it's an admission that you don't have an explanation. It's like asking why the sky is blue and being told it just is. Technically true, but not enlightening. Science seeks mechanisms, processes, physical reasons. Simply declaring uniformity as an initial condition doesn't provide any of these. It leaves the mystery intact. It admits defeat before the battle even begins. Another proposal was that maybe there were causal processes before the Big Bang that established uniformity. Maybe the universe existed in some form before the hot, dense state we call the Big Bang. Maybe it was contracting. Maybe it bounced. Maybe it cycled through expansions and contractions. During these earlier phases, regions could have communicated, reached equilibrium. Then, when the Big Bang happened, this equilibrium persisted. The uniformity we observe today is inherited from an earlier epoch. This is an interesting idea, and there are models along these lines. Cyclic cosmologies, bouncing cosmologies, pre-Big Bang scenarios. But they all face challenges. For one thing, entropy. If the universe went through a contraction phase, entropy would increase. The second law of thermodynamics tells us entropy always increases in closed systems. So, a contracting universe would become more disordered, not more ordered. How do you get the low entropy uniform state at the Big Bang? Some cyclic models try to address this by having entropy reset at each cycle, but this requires new physics we don't understand. It's replacing one mystery with another. Additionally, general relativity predicts singularities, places where the curvature becomes infinite and physics breaks down. Avoiding these singularities requires modifying general relativity or invoking quantum gravity, neither of which we have a complete theory of. So, while pre-Big Bang scenarios are worth exploring, they don't solve the horizon problem in a clean, well-understood way. A third attempt involved modifying the laws of physics in the early universe. Maybe gravity worked differently. Maybe the speed of light was different. Maybe there were extra dimensions that allowed regions to communicate in ways we don't normally consider. These ideas are speculative, and most of them create more problems than they solve. Changing fundamental constants or laws affects everything. All of the successful predictions of the Big Bang model, nucleosynthesis, the CMB temperature, the expansion rate, all of these depend on the laws of physics being what we observe them to be. If you change the laws to solve the horizon problem, you risk breaking everything else. There's no evidence that physical laws were different in the early universe. All our observations suggest the laws are constant. So, modifications to fundamental physics are a last resort, something to consider only if all other options fail. And in the case of the horizon problem, there's a better option. Inflation doesn't require changing the laws of physics. It works within general relativity and quantum field theory as we understand them. It's an elegant solution that fits naturally into our existing framework. Enter inflation. The idea was proposed by Alan Guth in 1980, while he was a postdoctoral researcher at Stanford. Guth was thinking about the magnetic monopole problem, another puzzle in cosmology. Grand unified theories, which attempt to unify the electromagnetic, weak and strong nuclear forces, predict that magnetic monopoles should have been created in the early universe. Lots of them. So many that they should dominate the mass of the universe. But we don't see any monopoles. Where did they go? Guth realized that if the universe underwent a period of extremely rapid expansion in its earliest moments, the monopoles would be diluted, spread so thinly that we'd never encounter one. The density of monopoles would drop to essentially zero. This rapid expansion is what Guth called inflation. And as he worked out the details, he realized inflation solved other problems too, including the horizon problem. If the universe expanded exponentially fast for a brief period, regions that are now far apart and apparently disconnected were once close together. They were in causal contact before inflation. They could reach equilibrium. Then inflation separated them, stretching them across vast distances. But the uniformity remained. It was locked in during the pre-inflationary phase when everything was connected. Let me explain how inflation works and why it solves the horizon problem. Imagine the universe at an incredibly early time, maybe 10 to the minus 35 seconds after the singularity. At this moment, the observable universe today, all 92 billion light-years of it, was compressed into a region smaller than an atom, much smaller, maybe 10 to the minus 26 meters across, a billionth of a billionth of a billionth of a meter. This entire region is causally connected. Light can cross it essentially instantaneously. All parts of this tiny region are in contact. They can exchange energy, reach thermal equilibrium, become uniform. This is crucial. At this early time, before inflation, the region that would become our observable universe was small enough to be uniform, small enough for physical processes to create uniformity. Now inflation happens. The universe expands exponentially, doubling in size every tiny fraction of a second. In less than a microsecond, this tiny region expands by an enormous factor, maybe 10 to the 60th, maybe more. After inflation, this region is huge, much larger than the observable universe today. It's been stretched from smaller than an atom to larger than a galaxy, or larger. The expansion is so dramatic, so violent, that it dwarfs all subsequent expansion. The expansion from the end of inflation to today is almost nothing compared to the expansion during inflation. Here's the key insight. When inflation ends, the universe continues expanding, but at a normal rate. The standard Big Bang expansion, Space grows, galaxies separate, light from distant regions takes time to reach us. But the uniformity established before inflation persists. It was imprinted on the universe when everything was small and connected. Then inflation stretched it across vast distances. Today, we see regions that are causally disconnected, regions whose light hasn't had time to reach each other since the Big Bang. But these regions were connected before inflation. They were part of the same small patch. They reached the same temperature, the same density, the same state. Inflation took that uniformity and expanded it to cosmic scales. This is why the universe is uniform despite appearing to violate causality. The uniformity was established when causality was satisfied. Then inflation stretched it beyond what normal expansion could account for. Think of it like this. Take a balloon and draw dots on it with a marker. The dots are close together. Now inflate the balloon. The dots separate. They move apart as the balloon expands. If you inflate it enough, the dots become very far apart. They're still on the same balloon, still part of the same surface, but they're separated by distance. An ant crawling on the balloon might never get from one dot to another because the balloon is so large. The dots are effectively disconnected for the ant, but they started close together. They were connected before the balloon inflated. The universe is like this balloon. Inflation is the rapid expansion. The dots are different regions of space. After inflation, the dots are far apart, apparently disconnected. But they started together. They were uniform before inflation separated them. This solves the horizon problem. The uniformity isn't miraculous. It's not a coincidence. It's a consequence of being connected before inflation and then being separated by inflation. Now, let's talk about the physics of inflation. What causes this rapid expansion? In general relativity, the expansion of the universe is driven by energy density. Normal matter and radiation cause the universe to expand, but the expansion decelerates over time. Gravity pulls things together, slows the expansion. But there's another possibility, a type of energy that causes acceleration instead of deceleration. This is called vacuum energy or dark energy. It's energy inherent to space itself. Empty space has energy. This sounds strange, but it's a consequence of quantum field theory. Empty space isn't really empty. It's filled with quantum fields. These fields have a ground state, a lowest energy state, but this ground state has non-zero energy. This vacuum energy has a peculiar property. It has negative pressure. Normal matter has positive pressure. It pushes outward. But vacuum energy has negative pressure. It pulls inward on itself. And in general relativity, negative pressure gravitates repulsively. It pushes space apart, causes acceleration. If the universe is dominated by vacuum energy, it expands exponentially. This exponential expansion is inflation. During the inflationary epoch, the universe was dominated by the energy of a quantum field called the inflaton field. This field was stuck in a high energy state, a false vacuum. While it was stuck, it acted like vacuum energy. Negative pressure. Exponential expansion. The universe doubled in size every fraction of a second. This continued for a brief period, maybe 10 to the minus 30 seconds. Then the inflaton field decayed. It rolled down to its true vacuum, its lowest energy state. When it did, the energy that was driving inflation got converted into particles and radiation. This is called reheating. The universe filled with hot, dense plasma. the standard Big Bang era began. From this point onward, the universe evolved normally, expanding, cooling, forming atoms, forming stars, forming galaxies, everything we observe today. But the brief period of inflation before this had enormous consequences. It stretched the universe, made it flat, made it uniform, created the conditions we observe. The details of the inflaton field are still uncertain. We don't know exactly what it is. It's not part of the standard model of particle physics. It's a new field, something we haven't detected directly. Different models of inflation propose different properties for the inflaton, different potentials, different couplings to other fields, different mechanisms for reheating. This is an active area of research. Physicists are trying to pin down the details. What drove inflation? How long did it last? How much did the universe expand? What happened during reheating? These are open questions. But the basic idea that inflation occurred, that it solved the horizon problem, that it explains the uniformity we observe, is widely accepted. The evidence supports it. The theory works. The predictions match observations. One of the most compelling pieces of evidence for inflation comes from the patterns in the cosmic microwave background. Remember those tiny temperature variations, the hot and cold spots? Inflation predicts these. It predicts they should exist, and it predicts their statistical properties. Here's how. During inflation, quantum fluctuations in the inflaton field get stretched to macroscopic scales. These fluctuations are tiny variations in the energy density of space. They're random, quantum noise. But inflation takes these microscopic fluctuations and expands them enormously, turns them into large-scale variations. When inflation ends and the universe transitions to the normal Big Bang phase, these variations become density perturbations. Regions that were slightly more energetic become slightly denser. Regions that were slightly less energetic become slightly less dense. These density variations are the seeds of structure. Over millions of years, gravity amplifies them. Dense regions attract more matter, become denser, eventually collapse into galaxies. Less dense regions lose matter, become voids. The cosmic web of structure grows from these primordial seeds, and these seeds originated as quantum fluctuations during inflation. The amazing thing is that inflation makes specific predictions about these fluctuations. It predicts they should be nearly scale invariant, meaning the amplitude of fluctuations should be roughly the same on all scales. It predicts they should be Gaussian, meaning their statistical distribution should be a bell curve. It predicts they should have a specific power spectrum, a specific pattern when you analyze them mathematically. All of these predictions can be tested by measuring the cosmic microwave background. And when we measure the CMB with satellites like WMAP and Planck, we find exactly what inflation predicts. The fluctuations are nearly scale invariant. They're Gaussian. The power spectrum matches. This is extraordinary. Inflation predicted these patterns before they were measured. It made quantitative predictions that were later confirmed. This is how science works. You propose a theory. The theory makes predictions. You test the predictions. If they're confirmed, you gain confidence the theory is correct. Inflation has passed this test. The patterns in the CMB match what inflation predicts. This is powerful evidence that inflation really happened. But inflation doesn't just solve the horizon problem. It solves several problems simultaneously. which is part of why it's so compelling. Let's talk about the flatness problem. The geometry of space, the curvature, is determined by the energy density of the universe. If the density is higher than a certain critical value, space curves positively, like a sphere. If it's lower, space curves negatively, like a saddle. If it equals the critical value exactly, space is flat. Measurements tell us our universe is very close to flat, within 0.5% of the critical density. But here's the puzzle. Flat geometry is unstable. In an expanding universe, any deviation from flatness grows over time. If the universe started slightly curved, it would become more curved as it expanded. For the universe to be so close to flat today, it must have been incredibly close to flat in the early universe. The density had to equal the critical density to extraordinary precision, 1 part in 10 to the 60th at the Planck time. This is extreme fine-tuning. It demands explanation, and inflation provides it. During inflation, the universe expands so rapidly that any initial curvature gets stretched flat. It's like taking a curved surface and expanding it until it appears flat. The surface of a sphere is curved, but if you zoom in close enough, it looks flat. A small patch of the Earth's surface looks flat even though the Earth is round. Inflation does this to the entire universe. It expands space so much that any initial curvature becomes negligible. After inflation, the universe is extremely flat, close enough to flat that even after billions of years of normal expansion, it still appears flat today. This explains the flatness without requiring fine-tuned initial conditions. Inflation naturally produces flatness. The magnetic monopole problem is also solved by inflation. Grand unified theories predict monopoles should form during phase transitions in the early universe. These monopoles would be stable, they wouldn't decay, and they'd be very massive. If they formed in large numbers, they'd dominate the mass of the universe. But we don't see them. Inflation solves this by dilution. Suppose monopoles formed before inflation. When inflation happens, space expands exponentially. The monopoles are spread out. The density of monopoles drops to essentially zero. In the entire observable universe, there might be 0 monopoles. Or maybe 1, so few that we'd never encounter them. Inflation doesn't prevent monopoles from forming. It dilutes them to undetectable levels. This is an elegant solution. It explains why monopoles aren't observed without contradicting the theories that predict they should exist. Inflation also explains why the universe is so large. Without inflation, the observable universe today would be only about a light year across. This is because the amount of expansion from the Big Bang to now, without inflation, is limited. The universe has been expanding for about 14 billion years at sublight speeds. That only produces a certain amount of expansion, not enough to explain the 92 billion light-year size we observe. Inflation solves this. The exponential expansion during inflation does most of the work. It expands the universe by an enormous factor in a tiny fraction of a second. After inflation, normal expansion continues, but it's minor compared to the inflationary expansion. The size of the observable universe is dominated by what happened during inflation. This explains why the universe is so big. There's one more prediction of inflation worth mentioning. Gravitational waves. During inflation, our quantum fluctuations don't just occur in the inflaton field, they occur in space-time itself. These are fluctuations in the fabric of space, ripples in the geometry, Just like fluctuations in the inflaton create density perturbations, fluctuations in spacetime create gravitational waves. These primordial gravitational waves would have been stretched to cosmic scales by inflation. Today, they should still be propagating through space, and they should have left an imprint on the cosmic microwave background. Specifically, they should create a pattern called B-mode polarization in the CMB. This is a distinctive swirling pattern in how the light is polarized. Regular density fluctuations create a different pattern called E-mode polarization. B-modes are unique to gravitational waves. If we detect B-mode polarization in the CMB, it would be direct evidence of primordial gravitational waves, and that would be strong confirmation of inflation. This is what the BICEP-2 experiment was looking for in 2014 when they announced a detection of B-modes. The announcement was exciting. It seemed like confirmation of inflation, but later analysis showed the signal was contaminated by dust in our galaxy. The B-modes they detected weren't primordial. They were foreground. The search continues. Other experiments are looking. And if primordial B-modes are detected in the future, it will be a major discovery. Direct evidence that inflation happened and a window into the physics of the very early universe. Not everyone agrees that inflation is the correct explanation for the horizon problem. There are alternative theories. There are debates about the details of inflation. Some physicists question whether inflation is falsifiable, whether it makes predictions that could prove it wrong. Others propose different mechanisms for solving the horizon problem. It's worth understanding these criticisms and alternatives because they show that science is an ongoing process. We don't just accept a theory and stop questioning it. We keep testing, keep challenging, keep looking for better explanations. One alternative is the ekpyrotic universe, a model where the Big Bang was caused by a collision between higher dimensional membranes called branes. In this scenario, the universe didn't begin with a singularity, but with a collision. The uniformity comes from processes during the collision. This is an interesting idea based on string theory, but it's speculative. String theory itself is unproven, and the ekpyrotic scenario doesn't make predictions as clear and testable as inflation does. Another alternative is variable speed of light cosmology, where the speed of light was much higher in the early universe. This would allow regions to communicate over larger distances. But as mentioned earlier, changing the speed of light has consequences that conflict with other observations. It's hard to make this work consistently. Some critics argue inflation is too flexible, that it can accommodate almost any observation, that there are so many different models of inflation with different predictions that the theory isn't really making specific testable claims. This is a fair concern. There are indeed many models of inflation, different potentials for the inflaton field, different predictions for details like the spectral index or the amount of gravitational waves. But all models of inflation share certain generic predictions, nearly scale invariant fluctuations, flatness, uniformity. These are common to all inflationary models, and these predictions have been confirmed. So, while the details might vary between models, the basic framework has made successful predictions. That said, the criticism is worth taking seriously. We should work to pin down the details, to distinguish between different models, to make inflation as predictive and falsifiable as possible. This is ongoing work. Physicists are refining the theory, making it more precise, connecting it to other areas of physics like particle physics and quantum gravity. Another criticism is the initial conditions problem for inflation itself. If inflation requires certain conditions to start, haven't we just pushed the problem back? Instead of explaining why the universe started uniform, we're explaining why the pre-inflationary universe had the right conditions for inflation to begin. This is sometimes called the regress problem, and it's a legitimate issue. Different models handle it differently. Some models say inflation is eternal, that it's always happening somewhere, and our universe is just a bubble where inflation ended. In this picture, there's no initial conditions problem because inflation has no beginning. It's eternal into the past. Other models try to show that inflation starts generically for a wide range of initial conditions, that you don't need fine-tuning to get inflation going. This is an area of active research and debate. There's no consensus yet. But even if inflation has its own initial conditions problem, it's arguably a simpler problem than the original horizon problem. We've reduced a complex mystery to a potentially simpler one. That's progress. What inflation tells us about the universe is profound. It tells us that everything we observe, all the structure, all the galaxies, all the stars, everything came from quantum fluctuations. Random quantum noise stretched to cosmic scales. The largest structures in the universe, superclusters of galaxies spanning hundreds of millions of light years, originated as microscopic quantum fluctuations smaller than an atom. This connection between the smallest scales of physics and the largest scales of cosmology is beautiful. It shows that quantum mechanics isn't just relevant for atoms and particles. It shaped the entire cosmos. It created the seeds from which everything grew. This is one of the most remarkable insights of modern physics. That quantum mechanics, developed to understand the atomic world, also explains the structure of the universe itself. Inflation also tells us that what we observe, the observable universe, is probably a tiny fraction of the total universe. If inflation stretched a small region into something much larger than the observable universe, then there's more universe beyond our horizon. Potentially infinite, regions we can never see because their light will never reach us. These regions might be similar to ours, or they might be different. If inflation is eternal, there could be infinitely many regions, infinitely many universes, each with potentially different properties. This is the multiverse hypothesis. It's controversial. Some physicists embrace it, others reject it as unscientific because we can't observe other universes. But whether or not you believe in the multiverse, inflation tells us the universe is bigger than what we see. The observable universe is just one patch, one small piece of a vastly larger whole. The horizon problem and its solution through inflation have changed how we think about cosmology. Before inflation, cosmology was largely about describing the evolution of the universe from some assumed initial state. After inflation, cosmology includes understanding how that initial state came to be. We've pushed back the frontier of explanation. We're asking deeper questions. Questions about the origin of structure, the origin of uniformity, the origin of the universe itself. This is exciting. This is what drives science forward. Each answer leads to new questions. Each solution opens new mysteries. Inflation solved the horizon problem, but it raised new questions. What is the inflaton field? How does inflation connect to particle physics? Why did inflation happen? What came before inflation? These are the questions physicists are working on now, and the answers, when we find them, will likely raise even more questions. This is the nature of science. An endless frontier, always pushing deeper, always seeking more fundamental understanding. The mathematical framework of inflation involves concepts from quantum field theory and general relativity that are worth understanding, at least conceptually. The inflaton field is described by a potential energy function, sometimes called the potential. This potential determines how the field behaves. Imagine a ball rolling on a hill. The shape of the hill determines how the ball moves. A steep hill means fast rolling. A gentle slope means slow rolling. The inflaton potential is like this hill. When the field value is high on the potential, it has lots of energy. As it rolls down toward lower values, it loses energy. The key to inflation is that the potential has a region where it's very flat, almost horizontal. When the inflaton is in this flat region, it rolls very slowly. This slow rolling is crucial because it means the field stays at high energy for a long time. And while it stays at high energy, it acts like vacuum energy. It drives exponential expansion. The universe inflates. Once the field rolls off the flat region and into the steeper part of the potential, inflation ends. The field oscillates around the minimum of the potential, converting its energy into particles. Reheating begins. The universe transitions to the hot Big Bang phase. Different models of inflation propose different shapes for the potential. Some have a single flat region, others have multiple flat regions or more complex structures. The shape of the potential determines the detailed predictions of the model. How long inflation lasts, how much the universe expands. The amplitude and spectrum of density fluctuations, the amount of gravitational waves. By measuring these properties through observations of the CMB and large-scale structure, we can constrain which inflation models are consistent with reality. Some models have been ruled out, others remain viable. This process of testing and constraining is ongoing. Each new observation refines our understanding, narrows the possibilities, moves us closer to knowing what really drove inflation. The quantum origin of structure is one of the most mind-bending aspects of inflation. Let me explain this more carefully because it's truly remarkable. In quantum mechanics, fields have fluctuations even in their lowest energy state. These are called vacuum fluctuations or zero-point fluctuations. They're a consequence of the Heisenberg uncertainty principle. You can't have a field with precisely zero value and precisely zero change. There's always some uncertainty, some quantum jitter. Normally, these fluctuations are tiny, microscopic. They have no observable effect on macroscopic systems. But during inflation, something extraordinary happens. The rapid expansion of space stretches these quantum fluctuations, takes them from subatomic scales to astronomical scales. A fluctuation that started smaller than a proton ends up larger than a galaxy. This stretching is so extreme that the fluctuations lose their quantum character and become classical. They transition from probabilistic quantum variations to definite classical perturbations in the density field. These classical perturbations are what we observe today as the temperature variations in the CMB and the distribution of galaxies in space. This process, Quantum fluctuations becoming classical through stretching during inflation is called quantum to classical transition. It's one of the few places in physics where we can directly observe the consequences of quantum mechanics on cosmological scales. Usually, quantum effects are confined to the microscopic world, atoms, particles, small systems. But inflation provides a window into quantum physics operating on the scale of the universe, the galaxies we see, the structure around us. All of it originated as quantum uncertainty, random quantum noise amplified by cosmic expansion. This is profoundly strange. It means the universe we inhabit, with all its order and structure, emerged from fundamental randomness, from the irreducible uncertainty built into quantum mechanics. This randomness was then processed by gravity over billions of years, forming stars and galaxies and planets. And on at least one of those planets, life emerged. We're here because of quantum fluctuations stretched during inflation. Our existence traces back to quantum noise in the first fraction of a second after the universe began. This is humbling and beautiful. The connection between inflation and quantum gravity is another frontier of research. Inflation takes us to extremely high energies and small distances, close to the Planck scale, where quantum effects of gravity become important. At these scales, space-time itself is expected to fluctuate quantum mechanically. The smooth fabric of space breaks down into a quantum foam, a seething mass of virtual particles and fluctuating geometry. We don't have a complete theory of quantum gravity yet. String theory and loop quantum gravity are candidates, but neither is fully developed or experimentally confirmed. Inflation provides hints about quantum gravity. The density fluctuations we observe came from quantum fluctuations of the inflaton field and quantum fluctuations in space-time. By measuring these fluctuations precisely, we're probing physics near the Planck scale. We're learning about how gravity behaves in the quantum realm. This is remarkable. We're using cosmological observations to learn about fundamental physics at energies we can never reach in particle accelerators. The universe itself is our laboratory for exploring quantum gravity. Some physicists have proposed that inflation might be eternal, that once it starts, it never fully stops. In this picture, inflation is happening somewhere in the universe at all times. Our observable universe is a bubble where inflation ended, where the inflaton field rolled down its potential and reheated, creating the hot Big Bang. But beyond our horizon, inflation continues. Other bubbles form, other universes with potentially different properties. This is eternal inflation. It's a speculative idea, but it follows from some models of inflation. If the inflaton potential has the right shape, quantum fluctuations can create regions where the field jumps back up to high values, even as other regions roll down. The regions that stay at high values keep inflating. The regions that roll down form bubble universes like ours. This process continues indefinitely. Inflation never ends globally, even though it ends locally in bubbles. If eternal inflation is correct, it has profound implications. It means our universe is one among infinitely many. A bubble in an eternally inflating multiverse. Other bubbles might have different physical laws, different constants of nature, different numbers of dimensions. This is the landscape of string theory, a vast space of possible universes, all realized somewhere in the eternally inflating multiverse. Not everyone likes eternal inflation or the multiverse it implies. Some physicists argue it makes the theory unpredictive. If anything is possible somewhere, then we can't predict what we should observe here. Any observation is consistent with the multiverse because some bubble will have that property. This reduces inflation from a scientific theory to an unfalsifiable framework. Others argue that even within the multiverse, we can make statistical predictions. We can calculate what typical observers should see, where most observers will find themselves. This is called the measure problem in eternal inflation. How do you count infinitely many universes and calculate probabilities? It's a hard problem without a consensus solution, but it's an active area of research. Physicists are working on it, and whether or not eternal inflation is correct, it shows that inflation as a theory is rich with implications. It opens new vistas, raises new questions, connects to other areas of physics like quantum mechanics, particle physics, and quantum gravity. The philosophical implications of inflation extend to questions about the nature of scientific explanation and the limits of empirical knowledge. If we live in one bubble of an eternally inflating multiverse, there are regions we can never observe. Universes forever beyond our horizon. This seems to place limits on what we can know through observation. We can't test claims about other universes if we can't see them. Does this mean such claims aren't scientific? Or does it mean we need to rethink what counts as scientific evidence? These are not easy questions. Science traditionally relies on empirical verification, observations, experiments, repeatability. But cosmology deals with a single universe. We can't rerun the Big Bang. We can observe only one realization of cosmic evolution. Inflation and the multiverse push these issues further. If other universes exist but are unobservable, are claims about them scientific or metaphysical? Different scientists have different views. Some embrace the multiverse, others reject it as beyond science. This debate is ongoing, and it reflects deeper questions about what science is and what it can tell us about reality. The impact of inflation on our understanding of time is also worth exploring. In classical cosmology, time has a clear direction. The universe begins at the Big Bang singularity. Time starts there. Before the Big Bang, there is no before. Time itself doesn't exist. But inflation complicates this picture. If inflation is eternal into the past, there's no beginning. Time extends infinitely backward. Or if inflation transitions from some pre-existing state, perhaps a contracting phase or a different vacuum, then the Big Bang isn't the absolute beginning. It's a transition point, a phase change in the evolution of a universe that existed before. This changes how we think about the origin of time. Maybe time didn't begin. Maybe it's eternal. Or maybe the question doesn't make sense. Maybe time as we know it only applies within our bubble. Other regions might have different time structures, or no time at all. These are speculative ideas, but they're taken seriously by physicists working on cosmology and quantum gravity. Understanding the nature of time at the deepest level might require understanding inflation and what came before. The role of observation in cosmology is unique compared to other sciences. In particle physics or chemistry, you can set up experiments, control variables, test hypotheses repeatedly. In cosmology, you observe what's there. You can't intervene, can't change the initial conditions and see what happens. This means cosmology relies heavily on statistical inference. We observe one universe, but we imagine an ensemble of possible universes generated by random initial conditions or quantum fluctuations. We calculate what typical members of this ensemble should look like. Then we check if our universe is typical, if the properties we observe are what we'd expect from generic initial conditions processed by inflation and structure formation. This statistical approach is subtle. It requires careful thought about probability and typicality, but it's powerful. It lets us test cosmological theories even though we have only one universe to observe. Inflation fits naturally into this framework. It predicts statistical properties of the fluctuations, amplitude, spectrum, distribution. We measure these properties, compare them to predictions. This is how we test inflation. Not by reproducing the Big Bang in a laboratory, but by checking if the universe we observe matches the statistical predictions of the theory. Understanding the horizon problem and inflation also changes how we think about the phrase, the beginning of the universe. Before learning about these ideas, most people think the Big Bang was the absolute beginning, time zero, before which nothing existed. But inflation suggests the Big Bang, at least the hot dense phase we usually refer to, wasn't the beginning. It was preceded by inflation, and inflation might have been preceded by something else. The beginning recedes into the past, becomes harder to define. Maybe there was no beginning. Maybe the universe is eternal in some sense. Or maybe the beginning is a quantum event that doesn't have a classical description. Maybe asking what happened before the beginning is like asking what's north of the North Pole. A question that seems meaningful but actually isn't because it presupposes concepts that don't apply. These are deep questions, and inflation, by solving the horizon problem, has brought them to the forefront of cosmological research. The future of inflation research is bright. New observations are coming, better measurements of the CMB, better maps of large-scale structure, gravitational wave detectors that might see primordial gravitational waves. All of these will test inflation in new ways, constrain the models further, rule out some possibilities, confirm others. There's also theoretical work, connecting inflation to particle physics, understanding how the inflaton fits into the standard model or its extensions, exploring the quantum gravity aspects of inflation, developing new models that make sharper predictions. This is an active field, hundreds of physicists working on these problems, publishing papers, debating ideas, making progress. And the ultimate goal is to understand not just that inflation happened, but why. What is the inflaton? What deeper principle explains inflation? Is it fundamental, or does it emerge from something more basic? These questions drive the research, and the answers, when we find them, will deepen our understanding of the universe and our place in it. Let me also address a common misconception about inflation. Some people think inflation explains the Big Bang, that it tells us what caused the Big Bang or what happened at the very beginning. This isn't quite right. Inflation explains what happened after the Big Bang, or more precisely, after the initial singularity in the first tiny fraction of a second. It explains how the universe went from a small uniform patch to the large uniform cosmos we observe. But it doesn't explain the singularity itself. It doesn't tell us why there's something rather than nothing. It doesn't address the ultimate origin. These remain open questions. Inflation pushes back the frontier of explanation. It reduces some mysteries to simpler ones, but it doesn't eliminate mystery altogether. There are still unknowns, still puzzles, and that's okay. That's what makes science exciting. There's always more to learn, always deeper questions to ask. The relationship between inflation and the anthropic principle is also worth exploring. If inflation is eternal and creates a multiverse with different properties in different bubbles, then we find ourselves in a bubble compatible with our existence. We couldn't be in a bubble where the laws of physics don't allow stars or planets or life. This is anthropic selection. It explains some features of our universe, not through fundamental principles, but through the requirement that we exist to observe them. For example, if the cosmological constant, the energy of empty space, were much larger, the universe would expand so fast that galaxies couldn't form, stars wouldn't exist, neither would we. So, we necessarily find ourselves in a universe where the cosmological constant is small enough for structure to form. This anthropic reasoning is controversial. Some physicists embrace it as a valid form of explanation. Others reject it as giving up on finding deeper principles. It's an ongoing debate. But inflation and the multiverse it might imply make anthropic reasoning more plausible by providing a mechanism for generating many universes with different properties. The experimental search for evidence of inflation continues with increasingly sophisticated instruments and techniques. The cosmic microwave background has been our primary window into the inflationary epoch, but there are other potential probes. One promising avenue is the search for primordial gravitational waves through B-mode polarization in the CMB. Several experiments are specifically designed for this. The BICEP and Keck Array telescopes at the South Pole, the Polar Bear experiment in Chile, the CLASS experiment also in Chile, the Simons Observatory being built in the Atacama Desert, and the proposed CMB Stage 4 experiment, which would involve multiple telescopes at different sites working together. All of these are pushing the sensitivity to detect the faint signal of primordial gravitational waves. The challenge is immense. The signal is tiny. Foregrounds from our galaxy are large. Dust emits polarized light that mimics the B-mode signal. You have to model and subtract this foreground carefully. Any mistake, and you might think you've detected primordial gravitational waves when you've actually detected dust. This is what happened with BICEP 2. The lesson learned was that we need better characterization of galactic foregrounds, multiple frequencies, better models, more data. The search continues, and if we succeed, if we detect genuine primordial B modes, it will be transformative. It will confirm inflation, measure the energy scale of inflation, open a window into physics at energies far beyond what particle accelerators can reach. There's also the possibility of detecting inflation through its effects on the matter distribution in the universe. The baryon acoustic oscillations, regular patterns in how galaxies cluster, contain information about the early universe. These oscillations are like fossilized sound waves from the hot plasma era. They're imprinted in the distribution of galaxies today. By mapping millions of galaxies and measuring these patterns, we can test inflation's predictions about the initial density fluctuations. Large galaxy surveys like the Sloan Digital Sky Survey, the Dark Energy Survey, and the upcoming Vera Rubin Observatory will provide enormous data sets for this. They'll map hundreds of millions of galaxies, measure their positions and redshifts. This data will test inflation in complementary ways to the CMB. Different systematic errors, different sensitivities. Together, CMB observations and large-scale structure observations constrain inflation from multiple angles. This multi-probe approach is powerful. It's harder to fool multiple independent tests than a single test. The theoretical landscape of inflation continues to evolve. New models are proposed. Old models are refined or ruled out. One class of models involves multiple fields instead of a single inflaton. These are called multi-field models. In single-field models, one field drives inflation. In multi-field models, several fields are important during inflation. They might affect the dynamics, create isocurvature perturbations, variations in the composition rather than just density. These models predict signatures that differ from single-field models. By looking for these signatures in the data, we can test whether inflation involved multiple fields. Another class involves non-minimal coupling to gravity. Usually, we assume fields don't directly affect the strength of gravity. But in some models, the inflaton couples to the Ricci scalar, a measure of space-time curvature. This coupling changes how inflation works, makes different predictions. There are also models where inflation is driven by the Higgs field from particle physics, the field responsible for giving particles mass. This is appealing because it connects inflation to known physics rather than invoking a new unknown field. These Higgs inflation models make specific predictions that are currently being tested. The connection between inflation and the early universe phase transitions is another active area. In the first moments after inflation, the universe went through several phase transitions, times when the state of matter changed. The electroweak phase transition, when the electromagnetic and weak forces separated. The QCD phase transition, when quarks confined into protons and neutrons. These transitions might have left observable imprints, gravitational waves, cosmic strings, or other topological defects, variations in the density field. By studying these potential imprints, we can learn about the transitions and indirectly about inflation. The transitions happened after inflation, but their details depend on the conditions inflation set up. The temperature, the density, the expansion rate. All of this was determined by how inflation ended, by reheating. So, observations of phase transition relics tell us about reheating and hence about inflation itself. Let me also talk about what inflation means for the fate of the universe. Inflation doesn't just tell us about the past, it affects the future. One of the key properties inflation gives us is flatness. As we discussed, inflation makes the universe extremely flat. Measurements confirm this. The curvature is very close to zero. Now, in a flat universe, the long-term fate depends on the energy content. If the universe is dominated by matter or radiation, it will expand forever, but the expansion will slow down. Eventually, everything will become cold and dark. Stars will burn out, galaxies will drift apart, black holes will evaporate through Hawking radiation. The universe ends in what's called heat death. A state of maximum entropy, cold, empty, dark. Nothing happens anymore. This is the most likely fate based on current observations. But there's another possibility. If dark energy, the energy causing the current acceleration of the expansion, increases over time, the expansion could accelerate faster and faster. Eventually, the acceleration becomes so strong that it tears apart galaxies, then stars, then planets, then molecules, then atoms, then space-time itself. This is called the Big Rip. It's a more violent end. Current observations don't favor it, but we can't rule it out completely. We don't understand dark energy well enough. It might be constant, like Einstein's cosmological constant. Or it might evolve. If it evolves in certain ways, the Big Rip is possible. Inflation doesn't directly predict the fate, but by setting the initial conditions, it constrains what's possible, a flat universe with dark energy. That's what inflation gave us, and that determines the range of possible futures. The cultural impact of inflation and our understanding of the horizon problem is also worth considering. When Einstein developed general relativity, it changed how we think about space and time. They're not separate, not absolute. They're part of a unified space-time that can curve and flex. When Hubble discovered the expansion of the universe, it changed how we think about the cosmos. The universe isn't static, it's dynamic. It had a beginning, it's evolving. Inflation similarly changes our perspective. It tells us that the universe we observe is just a tiny patch, a bubble. There might be infinitely more beyond our horizon. It tells us that quantum mechanics shapes the cosmos, that randomness at the smallest scales determines structure at the largest scales. It tells us that the first fraction of a second determined everything that followed. These ideas are profound. They change how we see ourselves, how we understand our place. We're part of a universe that's far stranger and more vast than we imagined. And that universe began in a quantum fluctuation, rose from fundamental uncertainty. This is a powerful story. It's awe-inspiring. It humbles us, and it connects us to the deepest mysteries of existence. Communicating these ideas to the public is challenging but important. The horizon problem is abstract. It requires understanding causality, the speed of light, the expansion of the universe. Inflation is even more abstract, exponential expansion, quantum fluctuations, reheating. These aren't everyday concepts, but they're important. They're part of humanity's understanding of the cosmos, part of our collective knowledge, and everyone should have access to this knowledge. Not just physicists, everyone. This is why science communication matters, why we make videos and write articles and give talks explaining these ideas. We're translating technical physics into language anyone can understand. We're sharing the wonder, the beauty, the profound insights. And when people understand, even at a basic level, they're enriched. Their view of the universe expands. They see deeper, think bigger, appreciate more. This is valuable. This is worth doing. And the response is always rewarding. People are fascinated by these ideas. They ask questions. They want to know more. They're hungry for understanding. This shows that science isn't just for specialists. It's for everyone. It's part of human culture, part of how we make sense of our existence. The horizon problem also serves as a case study in how science works. A mystery is identified. The universe is uniform, but shouldn't be. This violates our understanding. Scientists propose solutions. Some fail, some succeed. The successful solution, inflation, makes predictions. These predictions are tested, confirmed. The theory gains acceptance, but questions remain. New puzzles emerge. Research continues. This is the scientific method in action, not a linear path from ignorance to knowledge, but an iterative process. Observe, hypothesize, predict, test, refine, repeat. Each cycle brings us closer to truth. Each generation builds on the work of previous generations, standing on the shoulders of giants, making progress. The horizon problem exemplifies this. It was recognized in the 70s, solved in the 80s through inflation, tested in the 90s and 2000s through CMB observations, confirmed, and now we're refining the details, pushing further, asking deeper questions. This is how science advances. This is how we learn about reality, through careful observation, creative thinking, rigorous testing, and collective effort. The Horizon Problem's journey from mystery to explanation is a testament to the power of the scientific method, and a reminder that there are still mysteries to solve, still questions to answer, still progress to make. Thank you for exploring the Horizon Problem with me. If this journey into cosmic uniformity expanded your sense of wonder about the universe, a like or subscribe really helps the channel keep investigating these profound mysteries. And remember, when you look at the night sky, you're seeing the result of processes that happened in the first trillionth of a second after the Big Bang. The uniformity you observe across billions of light years was established when the entire observable universe was smaller than an atom. Inflation took that tiny uniform patch and stretched it into the cosmos we inhabit. This connection between the smallest and largest scales, between quantum fluctuations and galactic superclusters, between the earliest moments and today, is one of the most beautiful stories science has ever told. The universe is stranger and more wonderful than we imagined. The Horizon Problem revealed this strangeness. Inflation explained it, and our understanding continues to deepen. Good night, and may you never look at the uniformity of the cosmos the same way again.